Okay, so this is a lecture on inference in belief networks that anticipates that you've watched the previous lectures on probability and belief network semantics. But we're going to be focused on inference in this lecture. So this is a simple example. It's a debugging domain, diagnostic domain in which we're dealing with hardware problems, bugs in code. These would be reasons for certain symptoms of malfunctioning. And then we've got some indicators that are symptoms of the malfunctioning. This network up here is encoding certain conditional independency constraints. So B is independent of H. L is independent of, in this case, E, F, conditioned on its parents, H and B. This network would have had to follow from a particular ordering, but it could have followed from any one of several orderings. For example, down here, it could have followed from an ordering, a construction ordering that we've talked about previously of H, B, E, L, F, D. But it alternatively could have followed from this ordering. In fact, it could have followed from yet a third ordering, H, E, F, B, L, D. So long as a node comes after all of its ancestors in the ordering, it's going to be something that's potentially consistent with that ordering. So here's a simple example that Bayesian networks are good at. We want to compute a joint probability over value assignments to H, variable B, E, L, F, and D. So all of the variables involved in this network. And here I just show an intermediate step. By the chain rule, we can start with the probability of H. This product gives us the probability of H and not B. This product gives us the probability of H and not B and E, and so forth. And so this is always going to be true regardless of conditional independencies. But given the structure of the network, probability of H is the same. Probability of B is independent of H. And so the probability of not B given little h is simply the probability of not B. The probability of E given H and not B is simply going to be the probability of E and H because E is independent of B conditioned on H. And so this version down here is with the conditional independencies in mind that are implied by this Bayesian network. And again, I think you're going to find that computing joint probabilities over the value assignments of a network's variable is pretty straightforward. It's just going to be typically a product, always going to be a product of conditional independencies that are found in the probability tables of each of the variables in the network. Here's another joint probability computation. Different values, but again, assignments to all the variables here. You can look at this intermediate step, which is true, always true because of the chain rule. But again, we simply come down here and the probability of not H is a trivial computation of 1 minus the probability of H. Probability of B is given in a table. Probability of E given not H is found in probability table for variable E, etc. You know, technically, if I wanted to represent this in terms of only probabilities that were stored, I might rewrite probability of not H as 1 minus the probability of H. But on exams, this is typically going to be too much of a hassle or assignment, so I'll typically won't rewrite that negation as this, unless I say otherwise. You don't need to do that. And the rest of this lecture, I probably won't be doing it either. Now, what about joint probabilities over a subset of variables? If we're dealing with a subset of variables in which there's a kind of closure. That is, if a variable is involved in the set, the joint probability, like F, then its parent must be as well. So F is involved in this, so E should be involved too, and if E is involved, then H is involved, and H has no parents. So this satisfies this closure property. We're talking about variables, and if a variable is involved, then all of its parents are involved. And that's a simple thing to rewrite too in terms of the probabilities found in probability tables. I would simply rewrite this as the probability of H times the probability of E given not H times the probability of F given E. So this would be a rewriting of that joint probability given the conditional independencies in this Bayesian network or belief network. Here's another joint probability involving these two variables only. It satisfies this condition that if something is involved, then its parent is involved too. And again, that's a simple rewriting of probabilities involved in the table. Same thing here. Let's look at this one, the probability of H and B and not L and D. Simply going to rewrite the joint probability as the probabilities involving those various values that are found in the probability tables. And you can confirm that. And you can confirm that for these other conditions, including this last one, the probability of H given not B. Because these two variables are independent, it's simply going to be the product of those two variables. A network can be disconnected. I don't think we've seen a disconnected network, but they can exist. So here I've just slightly modified the other Bayesian network, although semantically it's quite different. One part is this lineage from H to F and B to D. It works the same way. If I ask about the joint probability of EHLB, if something is involved, then its parent is involved as well. That's simply going to be a rewriting of those probabilities. Just remember, this is a different network than the one we've been using typically. We'll go back to the original network. And what about joint probabilities of connected variables with unassigned parents? So we might ask about the joint probability of E and not F, which are these two variables. But in this joint probability, H, which is a parent of E, is not present. Its value is not assigned in this joint probability. What we want to do in this case is expand the scope of the involved variables to include the ancestors of the assigned variables and then sum out those unassigned values. So what am I talking about there? There's the joint probability. We know we can always rewrite a joint probability as conditional probability times the probability of the conditioning information. So I can rewrite this joint probability as this product. But unfortunately, the probability of E is not found anywhere in this network. The only probabilities involving E are, as information to be predicted, is in the probability table of E. Probability of E given H, probability of E given not H. So what I want to do is I want to involve H, and I want to expand the scope and rewrite the probability of E as the probability of E and H plus the probability of E and not H. So these are mutually exclusive conditions, E and H and E and not H. And so if I sum those two probabilities, these are basically going to be all the conditions that involve E. And that's going to give me, if I sum those two probabilities, that would give me the probability of E. And again, I can rewrite these two easily because they involve variable and its parent, and the parent has no ancestors. I can rewrite each of those as a sum as a product of probabilities that are found in the probability table. So I can plug that in, and the probability of E given not H is going to be this expression. This is only in terms of probabilities found in the Bayesian network, and this is the kind of answer I'm going to typically expect on an exam. Only rewriting joint probabilities is only those that, as equivalent expressions that only involve probabilities found in probability tables. Here's another example of a probability in which a joint probability in which a parent is not involved, probability of L and D. L's parents, H and B, are not involved here. Again, I can always rewrite this as this. This is found in a probability table. It's the only way of including a prediction, a probability for D given conditioning information here, so I know it's going to be involved because I find it in the joint probability. But how about this, probability of L? Again, I could expand this, but I want to expand it in a particular way. I want to expand it so that L's parents are involved in these joint probabilities. So the probability of not L is the sum of the probabilities of not L and all the possible patterns of H and B that might exist. So the sum of these probabilities. And again, I can rewrite these probabilities in terms of, because now these involve the parents that have no ancestors. I can simply rewrite each of these expressions as a product, and this is what I get. And so again, this would be the expression of this joint probability only in terms of the probability tables found in the belief network. Instead of pulling this out right away, I could have simply expanded the probability of L and D and summed over, expanded to the parents of L in this case, and involving and looking at the probabilities of not L, not D, and all possible patterns of H and B here. So there's a typo here. I'll fix it before I put the slides online. But all those possible patterns would be H and B, H and not B, not H and B, not H and not B. And again, I'll make those adjustments down here as well. It looks like in this final version, I do have I've updated I updated the copy and paste appropriately. So here we find the HB pattern, the H not B pattern, not HB pattern, not H not B pattern. So this is a final correct answer, but there's some typos up here that again I'll correct. I'm not gonna be probably asking you on exams to state a precise algorithm for doing this. I'm only going to ask you to do hand simulations of computing equivalent expressions for joint probabilities, and soon we'll be looking at conditional probabilities as well. But you might imagine starting with a query up here, decomposing it in the way that we have talked about, using values that we find in tables for some of the involved variables. But then for some of the other involved variables, expanding the scope into a collection of joint probabilities that involve the parents and all the ancestors as needed in these joint probability computations, and then rewriting each of those. And so you can imagine doing a depth-first traversal of a tree. So I take that, I expand it to that, I take that, I expand it to that, I take that, I expand it to that. Doing table lookups, getting these values, and then using a cumulative product to compute that value. And then up this level, using a cumulative sum to compute over these levels, and then multiplying nodes at this level. Alternatively, I could have, again, taken this and immediately expanded into the parents involving patterns of H and B here. And these are correct in this case. I have to have all possible patterns of H and B there. But it looks like I've forgotten a not D there, so that's another adjustment I'll make before posting the slides. And again, you could rewrite this, and this term is going to be common across all of these, and so at a later time I could pull that factor out. Here we're given an example that's like the previous problem, but one of L's parents is got a established value in this case. In this case, we're not going to be summing over all possible values of H and B because B's value is set here. So we just have to sum over different values of the H variable, H and not H. So we can rewrite this probability as this. The probability of B and not L is going to be the probability of B and not L paired with H plus the probability of B and not L paired with not H. And again, this would give me a set of terms that are only in terms of probabilities found in the BN tables. If you need a little bit more explanation here about this equivalence, then you can look down here at the slides later. Here's a probability, compute the probability over a single variable, E in this case. Same kind of thing applies. E can be written as E paired with H, E paired with not H, making sure that I'm pairing. I'm introducing E's parent here and then rewriting those in terms of probabilities found only in the probability tables. E and L, let's take a look at the joint probability here. This is somewhat different than we've seen before. These are not directly connected. But in this case, if I want to compute the joint probability of E and L, I would still expand the scope of this joint probability to involve patterns that include all the parents of both E and L. So I would be introducing H and B, and I would be summing over all patterns of H and B. And this sum is going to give me this joint probability. Here I've just asked you to finish this, rewriting each of these joint probabilities into probabilities only involving probability tables. Again, a network can be disconnected, but this rule of summing over ancestors still applies. The probability of E and L in this case, same joint probability, same joint probabilities summing over E and H, H and B there, rather, which are still the parents of E and L here. And I can rewrite this in terms of probabilities only involving probabilities found in the probability tables. If you need a little bit more explanation, this explanation goes through the chain rule, which always applies, and then rewriting these probabilities in terms of only those that are found in the probability tables. So, you know, after you've practiced a bit, you almost certainly know how to compute joint probabilities. So how about computing conditional probabilities? Here's a conditional probability, the probability of L given H and B. And these conditional probabilities are going to be useful for doing diagnosis, predicting causes from effects and effects from causes, symptoms from diseases, for example. So here's a conditional probability, and in this case, it's essentially table lookup. Again, on an exam, you can state this directly, but in terms of the probabilities that are actually found in the probability tables, this would be equal to 1 minus a probability that was actually found in the probability table. But it's essentially still a table lookup. Again, if the network was constructed so that H and B are causal, perhaps these are diseases, this forward direction of inference would be essentially going from causes to effects, or in this case, an intermediate variable that might lead to something which is directly observable. Here's another example of a conditional probability, the probability of D given H and B. A conditional probability can always be represented as a joint probability, two joint probabilities. The probability of all of these value assignments, the joint probability of that, divided by the joint probability of simply the conditioning variable assignments. So you can take this conditional probability and translate it into a fraction involving a ratio involving two joint probabilities. And of course, we know how to solve joint probabilities now. And so you can solve each of these independently. So this D, H, and B would involve this, we would have to expand this set of variables to fill the gap between these two. And in this case, filling the gap would involve including variable L. And variable L, we don't know variable L's value, but it has two possible values because these are all binary valued variables. These two joint probabilities, sum over them, and I get this joint probability. Again, I can rewrite this. I'm going to skip this intermediate step that uses the chain rule to write this and go to probabilities that are found directly in the probability tables. So the probability of D given L, probability of L given H and B values, and then the joint probability of H and B. And I could rewrite that as simply the probability of H times the probability of not B. I don't need to in this case because you can see that after rewriting this expression and rewriting this expression and dividing by the probability of H and not B, these are going to cancel. Factor this out and then it cancels with the denominator. And what I get in this, and this is intuitively appealing because the probabilities of H and not B are fixed in this expression. And you notice that there is no reference to the probability of H and B in this expression because they have been fixed. It's as if their probability is 1 because they have a particular, the values have been picked, set to a particular value down here. Another example of a conditional probability, again, going from causes to effects. I can rewrite that as two joint probabilities, F and H and H. This, of course, is given in the network. This can be rewritten by filling the gap and involving variable E here, both its values, and then summing over those. So these are the expressions in terms of only the probability tables. And again, the probability of H's cancel out, which in this final expression is indicative of the fact that H's value is already set. So the probability of H, or the probability of any H, particular H value is not relevant here because we know its value. It's little h. Here's yet another probability. In this case, we are given only one of the parents, and we are going to still have to involve the other parent. We can rewrite this as the joint probability of not L and H divided by the probability of H. But there is no probability of L given H in our probability tables. We only know the probability of L given H and B values. So I'm going to have to involve B here and look at the different values, possible values of B. Again, this sum is going to be equal to this. And I expand that out just like I've done before. The H values cancel, and I'm left with the sum that doesn't reference the probability of H, again, because it's been set. We can also reason, we've been reasoning from causes to manifestations. We've been reasoning in this direction, but we can also reason in the other direction. Given symptoms or manifestations, we can reason about the causes or the possible causes. Again, I can simply rewrite this as two joint probabilities and then solve those independently. H and F, I would seek to fill the gap here with the E variable. And this would be a sum involving both possible values of E. I could rewrite those quite easily because I now have all those variables in terms of only probabilities that are found in the probability tables. Expanding F out, the probability of F in the denominator here, I would rewrite this as probabilities involving F and its ancestors, all possible patterns of its ancestors, E and H, E and not H, etc. here. And this sum would give me the probability of F. And again, I can rewrite each of these in terms of only probabilities involved in the probability tables. You'll notice in that example that we just did, probability of H given F, that there is some repeated computation. And repeated computation can happen even more with inferences in expanding probabilities as we've been doing. So for example, in looking at the numerator, I'd computed this joint probability, but also in computing the value of the denominator, I'm going to compute that joint probability. In the numerator, I computed this joint probability, and in the denominator, I will compute it later. And so techniques that cache results are going to be are one way of making this inference procedure more efficient so that we don't have to do repeated computations. In this case, the repeated computations wouldn't be bad, but you can imagine in more complicated examples that there might be a lot more repetitious work that we could save and save cost by caching results and reusing the results of those computations. One last sort of interesting class of examples is illustrates a concept of conditional dependence. We've always been talking about conditional independence when talking about Bayesian networks. But in doing inferences, we often stumble upon conditional dependencies that are going to be caused. I'm going to lay some groundwork for this. I want to compute and the idea is that, let's say these are two possible causes for this, or for some outcomes here are causal of some outcomes here. If we know that this is true, if we know that there's a particular value assignment of this, and then I'm later told about a particular value assignment of this that's causal of the value assignment for this, it's going to change the probabilities, the posterior probabilities of the alternative explanations for why we might have a value assignment there. I know that might be a little bit hard to swallow, but a little bit much to swallow, but we'll look at a couple of examples. So let me just lay a little bit of groundwork here. What's the probability of H given L? A particular L value in this case. I just solve this the regular way. That's the joint probability divided by the probability of conditioning information, and I would get this. I would, if I was trying to compute the exact probability, I'd expand this to probability of L to in the way that we've seen in terms of joint probabilities over parents as well. But for purposes of my point, the point I want to make here, we don't have to. The probability of B given L, we can do the same thing. It's going to look very much the same as this with different values. Still looking at the background for illustrating this idea of conditional dependence. What's the probability of both H and B given L? I can rewrite that this way. And then rewrite this in terms of only probabilities found in the probability tables. Again, I would expand that out if I was looking for an exact value there, but for purposes of this illustration, I don't really have to. And so the question is, these two values were values I computed on the previous slide. If the independence of H and B was retained after conditioning on L, then this would be true. This is a definition of the conditional independence of H and B conditioned on L. This is an alternative and equivalent definition for the independence of H and B conditioned on L. That is, if I know L, B adds no additional information to the probability of H beyond what L conveyed. And again, this is another definition of the conditional independence of B and H conditioned on L. If these were true, then this would indicate that the independence of H and B was retained after conditioning on L, but these equalities are not true. And so knowing L induces dependence on H and B. And I went through this brief explanation earlier. If L is known and we additionally are told H, this changes the probability of B and vice versa. This is just an illustration of this value here, you can look at that and verify it later. But this notion of conditional dependence might be something we return to later. It's an important concept. Just an aside, this is some background on, if you need more explanation on these equivalences that we talked about. That is, we talked about this being one definition for conditional independence and this being another definition of conditional independence. And there was yet a third, but you would show the equivalence this way, that given one, you could derive the other through equivalency transformations applied to both sides. So you can follow this later. So we're all done with this lecture, but I want you to take a look at this network, and we'll be giving you some other example networks and see if you can figure out some of these conditional independencies yourself. And of course, be familiar, to do these, you'll have to be familiar with joint probability, solving joint probability as well. So that's it for today's lecture. And next we'll talk about sequential decision-making with probabilistic networks.